I think it's meant to start in 7 minutes from now.
Okay. Maybe we can wait a little bit if someone else is coming.
Yep, sure.
Okay.
So how has the conference been for you so far, Rosaria?
Sorry.
How has the rest of the conference been so far for you?
I think very interesting, and for me, this session is interesting because I recently have been involved in some project here at the Parliamentary Budget Office on the impact of energy prices on households spending.
Yeah.
So because we wanted to test if there's some change in the.
And I think that the data is sort of coming up slowly, but well, I think the expectation is that the price hasn't actually changed consumption as much as anyone expected. So yeah.
Yeah. In our estimation, we use a fixed consumption button for now, but we wanted to, test if we can use some sort of price elasticity and to compare the estimation with and without including the price elasticity.
Okay. Interesting.
Did you find the symposium interesting for you?
Yeah. There's quite a range of topics, and I think it's always quite educational to attend the sessions of stuff that I don't normally do. So then you get to see what else is out there, really.
Yeah. Even though it's not your topic, so at least you can, see.
Yeah. Exactly, and
the issues the other are.
Yeah, and everything is so relevant to the current global situation, so everything is useful.
Yeah. Right.
Yeah.
Are you reading, right?
Yep.
Now? No. Oh.
Yeah.
Sorry, if you want, can we start now? Okay.
Okay, so good afternoon, everybody. I wanted to welcome all of you to the afternoon session of the 7th Symposium on Energy Security. This session is on resilience in the electricity market, and I want to give you some piece of information on the presentation. You have total of 18 minutes for the presentation, and in order to have at the end of the session some minutes for question that may arise for the floor. So please, Jieyang, excuse me for if I mispronounce your name. The first presentation is on time-varying price elasticity on the electricity demand, joined with Jacopo Torriti, and you present a new econometric approach on the estimation of intraday patterns in price elasticity of electricity demand. So please, the floor is yours.
Thank you. Yeah, my name is Jieyang, and this is joint work with Jacopo Torriti. We're from the University of Reading. Oh, where's my... There, okay. So just a quick few words on the idea behind what we're doing here, which is that flexibility in energy demand is something that is quite ideal for various reasons. If we're looking at lowering carbon emissions or working towards net zero, it's useful. If we're looking at reducing overall prices for consumers, that's useful. If we're looking at reducing the strain on the grid at certain times, that also can be useful, although that's not so much looking at peak reduction, but at critical event sort of situations. But just to sort of highlight how it's useful, so I have here a plot of energy generation by fuel source for Germany this year, January until late November. And I really just want to focus on the highest line, the one that dominates everything else. That one is fossil fuels. So there's obviously quite a lot of fossil fuels being used here, in Germany at least. And we see that there are two sort of peaks in the morning and in the evening. Those typically are when prices are the highest. Fossil fuels are the most expensive to use, really. And that's also obviously related to carbon emissions. So if we can reduce the peaks, we can sort of reduce carbon emissions and hopefully sort of drive electricity generation to times when you could use solar or other types of cleaner sources. So how do we do that? How do we look at intraday flexibility? If we want to reduce consumption at certain times, we could look at technological advancements. So whether it's automation or more efficient appliances, whether we're looking at smart devices that you could sort of, from the office, you could tap a button on your phone and start something running at a time when price is cheap and price is clean. When electricity is cheap and clean. Or if we look at storage, that's a sort of thing where you could generate when it's clean and store it and use it when otherwise you would be using coal or gas or any other dirty, expensive fuel source. So that's technology. Another way to get flexibility in that sense is to disrupt societal rhythm. So here we're looking at things that society does that tends to be synchronized. So for example, people seem to, for obvious reasons, generally cook and prepare dinner at a certain time of the day, watch television after coming home from work, that sort of thing. And it's generally a quite synchronized sort of thing. The television shows come on at the same time. Cooking happens roughly at the same time because people either get ready for work or come home from work and need to start doing that. So changing the timing of those activities. But what we're looking at here is the financial incentives. So there are ways in which there is a hope that different levels of prices throughout the day might affect consumption. And we see that in the form of real-time pricing or time of use pricing, critical peak prices, critical peak rebates. So anything that generates some sort of difference in prices between, say, noontime and 7 p.m. That's something that is hypothesized to potentially induce flexibility, so force people to behave in a certain way in reaction to those price differences. Now, whether or not that actually happens should be measured. How do we figure out, let's say before we want to introduce some sort of price intervention, how do we figure out how much to perturb the price, how much to change the price in order to achieve a certain outcome in terms of demand reduction? Or alternatively, if you've already done this, you're looking at historical data, you could look at how much it has actually worked. So we need to figure out how to measure it, and one of the most common ways of measuring sort of price and quantity effects is price elasticity of demand in this case. So it's just the percentage change in quantity demanded divided by percentage change in price. It's a fairly simple sort of concept. Now, in the literature, in terms of sort of econometric modeling to estimate this quantity, quite a lot of methods have been used. And I said here they're not mutually exclusive because, for example, in semi-parametric models, we've got Gao et al. 2021. Yes, they use semi-parametric models to introduce some sort of time-varying parameter, but they also account for endogeneity using two-stage least square. So you've got Gao 2021 there as well. So they're not mutually exclusive, where relevant and where appropriate to sort of mix and match. But these are some of the methods that have been used. Now, just a quick slide on what's different in this study that I'm presenting today is that we use intraday data. Very, very few studies have done so. It's necessary for this kind of study because if you're looking at, time varying elasticity, but varying within the day, so you get different elasticities within the day, then you need obviously data that has intraday intervals. If you use daily data, monthly data, you can't get that sort of thing. So we use intraday data. We're one of the very few papers to look at it in any capacity. We also introduce here a test to first of all check whether or not price elasticity is constant. Because if it is constant, then what's the point of doing this? Go back to the more basic methods that have been used already. But if we do reject the null hypothesis, then we propose a method to estimate this time varying price elasticity. I've put here 2 additional points, which will become a bit clearer later why they're different from the literature. But I've said we use a single model for the whole sample instead of splitting the sample into different subsamples. And we ensure that the estimated price elasticities are smooth. So these 2 we'll come back to a bit later. But essentially, the most basic kind of model is a linear model. So in this, we have quantity on the left-hand side. So either in logs or levels, we've got quantity, and then at some sort of intercept. Here, the key variable, the explanatory variable of interest is price. And whether it's in logs or levels depends on, the econometrician. But then we use only levels because we have negative prices, so we can't do logs. So quantity depends on some intercept, on price, and then on some other exogenous covariates. The coefficient of interest is C, the coefficient on price. And in this specification here, it is a constant. So we haven't gone into this time varying elasticity idea. We're just looking at how to even estimate elasticity in the first place. And this is something we have that has been used. So this was the most basic model that has been used a lot. Now, if we want to let the coefficient be time varying, if we want to let elasticity change across time, then we could use a state space type model. So the first line here, the first equation is almost exactly the same as before. The only difference is that the coefficient C now also depends on time, and how that changes is governed by this next line. So it's an autoregressive process. And this is often estimated using Kalman filter models. Alternatively, if you want to let it vary smoothly across time, you could have a semi-parametric type model where instead of CT, I've put here F tau. So some smooth unknown function of tau being essentially a function of time. So that here we've got two modifications to the basic model. Both of them let the coefficient change across time. But what happens here is that there's no restriction on how they change really beyond what's given here in the state space model. What I mean by that is if we're looking at trying to estimate price elasticity at 1 o'clock, so we want from some larger sample, we want to figure out what is price elasticity at 1 o'clock in the morning. This won't give you that. This will give you 1 o'clock on the 1st of January. It'll give you a different thing at 2 o'clock, 3 o'clock, and then the next day, there's no restriction that 1 o'clock the next day is the same as 1 o'clock today. So it just moves freely in a sense. That's not what we are trying to look for here. We're trying to look for a repeating daily pattern. So I guess before that slide, just quickly, this slide, the 2 models on this slide have been used, but they have generally been used on sort of monthly data upwards, so monthly, annual, quarterly data sort of thing, and they sort of essentially tell you how the trend evolves across time. Doesn't give you some sort of daily pattern, which is what we're hoping to find. So if we turn now to higher frequency data, sorry, I've got to cough if I can't find the mute button. Sorry. Right. So using intraday data instead. Now forgetting about the time variation, just looking at intraday for a bit. There's one paper that estimates price elasticity using intraday data. Sorry, there's not one paper. I've highlighted one paper. This one looks at constant price elasticity. So it fits the basic model from before to the whole sample and returns some estimate of price elasticity of demand. one value for the whole sample. If we look down here, we've got a couple of papers that do look at intraday variation, Fun and Heinemann 2011 and Knaut and Paulus 2016. Both of them, now the difference is that they treat each intraday interval separately. So if it's hourly data, for 1 o'clock in the morning, they take all the 1 o'clock in the morning data and only that, and they fit it to a model. And then they get an estimate for price elasticity and they say, okay, that's the 1 o'clock in the morning elasticity. That's out of the way. Then they take the 2 o'clock data, all the 2 o'clock in the morning data for their full sample, and they fit a model there, and they get price elasticity and so forth. So then they get some intraday pattern, which is based on independently fitting each intraday interval to one model. So if we look at this equation here, it's the same as before. The only difference is that now I've got a subscript h on every single term. So whether it's a coefficient to be estimated or whether it's data, they've all got an h there, and that just shows that you've completely separated all of the intraday intervals. So that is in contrast to Leeson, which takes the whole sample together. So these guys are looking at separately each intraday interval, whereas the top one, the constant one, looks at everything together. Now, the ones that do produce some intraday pattern, they don't actually justify doing so. They give you that pattern, but they don't give intuitive reasoning why. They don't produce some statistical test as to whether it's valid or not. So what we're proposing, the aim of what we're proposing, is first of all to test whether or not this variation even exists. If it's constant, then there's no point going ahead, just use a constant model. But if we test and we show that that there is some variation, then we want to estimate that variation. So how do we do it? We augment the basic model. So we take the basic model and we just add some terms to it. Here, this equation here essentially nests that basic model. If we take all the red terms out, it's the basic linear model. What these red terms do is they introduce some daily patterns. So I've got here this capital H, and that is to represent the number of intraday intervals. So if it's hourly data, that's H will be 24. If it's half hourly data, it'll be 48, and so forth. So it depends on the size of your intervals.
Sorry, Jieyang, you have 4 minutes left.
Ah, okay. Sure. So the other thing is that these will preserve smoothness also in those patterns. Now I've got capital S here. We need to choose that. And the way to do that is I set S equal to 1. And then I test delta, I test gamma. And if at least one of them is significant, then we know that these terms play a part, therefore there is variation. So that's the test, and it's nested in the model itself. So and then we increase S to a point where it stops being significant. And then that's how many S's we choose, and that will determine how smooth elasticity is. So just very quickly, how to get price elasticity from the coefficients. I've got a table here. I'm just showing constant and time varying, which is what we've discussed, and just also whether it's linear quantity demanded or log quantity demanded. There's a slightly different formulation, but it's very simple to do, and we can see that. The difference here for time varying is that we take the average of only the relevant hours, and that's all. But the coefficients and everything are estimated from the full sample. Here's the full model. I'll probably skip this, just wanted to show all the variables that are there. For the data, we've got just a quick summary here. So like I mentioned, we have negative price, therefore we can't take logs of prices. But everything else looks fairly normal. So the heating degree day, cooling degree day, all of this looks fairly standard. And this is the output. So just what I want to highlight here is these cosine and sine terms. We have large enough t-stats that we get significance up to capital S equals 2. So that is a test that shows that yes, there is variation, and this will return to you the variation that exists in the price elasticities. And here's a plot. So just quickly, I've described 3 methods. There are 4 lines here. The blue line is for constant elasticity. The orange line is the one that we are proposing, and that's the smooth looking one. What it shows is that price elasticity is lowest. So the higher the line, the lower elasticity, because it's on a negative scale. So it's lowest at the rush hours in the morning and in the evening. Now that's in contradiction to the purple line, which is what you get if you estimate each hour separately. And the purple line is the methods that have been used in the literature in 2 papers before. So obviously we are in contradiction with them. I'll leave the yellow line out for time. So we are in contradiction to what the literature says in terms of previous attempts in econometric modeling, but we actually agree on some level with this other paper that looks at flexibility in the UK. Now, it's not based on price elasticity, but Authority creates an intrinsic flexibility index and finds that in the UK, at least, flexibility is the lowest at 7. Yep. So smoothness relies on aggregation. Shan't spend time on this, but essentially, if you have an aggregate data set, then consumption will be staggered. So cooking happens gradually across all the households. But if you look at individual household level, I don't expect it to be smooth. There are some other gaps that have not been addressed and I haven't addressed, maybe avenues for future research. And that's all. Thank you.
Thank you for the interesting presentation. So now the floor is to Judith Stute from the Fraunhofer Research Institute for Energy Infrastructure and Geothermal System. She will present a paper on the current development on the Germany day-ahead spot market, curse or blessing for the utilization of flexibility by households. Please, Judith, the floor is yours. 15 minutes, 15 to 18 minutes.
Okay, thank you very much for the introduction. Yeah, I'm happy to present my work today with the topic that we already heard right now. So let's get right into it. Yeah, so first I want to give a short introduction into the motivation of the work and the underlying research questions of the study. Yeah, in the past few months, we saw a sharp rise in the day-ahead spot market prices in Germany, but also in other countries in Europe. On the right-hand side here on the slide, you can see the box plots of the day-ahead spot market prices for 2019 on the left, and for the time from October 2021 to February 2022 on the right-hand side. As you can see, the prices did rise on average, but also the price spreads did increase. Yeah, and as most household customers in Germany already realized, this does have an effect on the household electricity prices. This means standard static electricity prices that are common in Germany, but also dynamic electricity prices that are to some extent already available on the market in Germany today. Yeah, therefore, the following research questions do arise. First, what are the effects of the changes in the spot market for the economic attractiveness of using a home energy management system combined with dynamic electricity tariffs for household customers? And derived from that, what does this mean for flexibility deployment of different technology assets in households, such as electric vehicles, heat pumps, or battery storage systems? Let me now briefly introduce the method, or better, the model we used in order to answer these research questions. For the study, I did use a self-developed, let's say, building flexibility usage model that incorporates different technology assets such as heat pumps, electric vehicles, battery storage systems, and PV systems. And within the model, we have 2 options. Option A is the inflexible operation of heat pumps, electric vehicles, and battery storage systems. This option is used to represent the status quo, so where most households in Germany do not utilize their flexibility and use a static electricity tariff. For this, we use a simulation model. And then there's option B. where we have a flexible operation of heat pumps, electric vehicles, and battery storage systems, with the assumption of the availability of a home energy management system. And this home energy management system minimizes the household's electricity bill. This model is used to represent the possibilities that arise through digitalization and dynamic tariffs. Here, a mixed integer linear programming optimization model is used. Results from the model are, on the one hand, the load profile of the individual assets and of the building as a whole, and the flexibility used when using option B, so the optimization. On the other hand, we have, it's possible to derive the economic effects of different tariffs on household electricity bills. After this insight into the model, I will now give a short overview on the underlying case study. So to speak, the assumptions that we made for households and the assets, but also the electricity tariffs considered. Let's start with the household settings. We do have 316 measured household load profiles, also with socio-demographic data of the households. We assume that the PV systems that are used do have an installed power which is dependent on the household's power consumption. The same is valid for the usable battery capacity of the battery storage systems. For electric vehicles, we do have a charging capacity of 11 kilowatts, and we do assign the driving or standing stopping profiles to households via socio-demographic data that we have for the electric vehicles, but also for the households. For heat pumps, we dimension them or define the size of the heat pump via the living space of the households and the heat demand of the building. Also for heating systems, we assume that we have air-water heat pumps with underlying heating curve and an outside temperature-dependent COP. And heating only takes place from fall to spring for temperatures below 15 degrees Celsius. Yeah, so now to the considered electricity tariffs. In order to analyze the impact of the current development on the day-ahead spot market on households, we did define 3 price scenarios that you can see on the slide. For each price scenario, we have a dynamic tariff and a static tariff. The dynamic tariff is derived from the day-ahead spot market prices, and the static tariff is represented by the mean value of the price time series of the dynamic tariff. On the left-hand side here, you can see the static tariffs for the 3 scenarios. We have a low, medium, and highest scenario. On the right-hand side, you can also see the dynamic tariffs for all those 3 scenarios. The plots show the average prices by season, type day, and hour of the day. So we can see that we have the lowest prices in the early morning hours and another price, let's say, valley around the afternoon. And in the background, the lighter color shows the range of min and max values for each hour of the day. So here we can see that we have higher price spreads during winter season, and during summer season, we do have the lowest price spreads. So how did we come up with these price scenarios? I only have 50 minutes, so I keep it short. So the first scenario, the low scenario, is basically the day-ahead spot market time series of the year 2019. And in order to get a good comparability between the scenarios, this time series was then manipulated to get the highest scenario, to map the KPIs of the day-ahead spot market prices of October 2021 to February 2022, as I showed before. So that means that we adjusted the mean value of the time series, the standard deviation, and the min-max values. in addition to the low and high scenario, we define a medium scenario, which just lies in between the other two scenarios here in green. Yeah, with that, I would like to present an excerpt of the results. So let's begin with the economic effects of the 3 price scenarios on households. Here you can see the share of households with a cost increase in blue and a cost reduction in green when using a dynamic tariff. And and when they utilize their flexibility compared to the static tariff and the inflexible operation case. Incorporated in the costs are the electricity costs, but also the additional costs for metering point operation and the investment in a home energy management storage systems. Those costs arise when the households opt for the dynamic tariff, because then they need this additional technology. Cost reduction means it would be beneficial for a household to opt for the energy management system and the dynamic tariffs. Cost increase means the opposite. For PV battery systems here on the left, opting for the dynamic tariff is not feasible because households with these assets do have a lower electricity bill in general because they already have PV and battery system. So it is harder for them to make up for the additional costs of the metering point operation and the investment in the energy management system. With the absolute cost savings they have. Electric vehicles, they seem to be able to make a great use of dynamic tariffs, even more when those households with electric vehicles also do have a heat pump system. You can see that on the right. We can also see that if the price or price spread scenario is higher, then this whole thing gets more attractive, or it gets more attractive to opt for those dynamic tariffs. For household with heat pump systems, we do only see some households which achieve a cost reduction in the high scenario. It's one household in the medium scenario. And in order to explore that further, I will focus on households with heat pumps in the following. So let's start by having a look at the average aggregated household load curves. You already saw this type of figure before. So again, it's the average for each hour of the day by season and type day for the household load in watts here. We see the static tariff case with no utilization of flexibility in gray, and the flexible cases for the 3 price scenarios in purple for the low scenario, green for the medium scenario or middle scenario, and brown for the high scenario. So we see that in winter, on the top right, for example, we see that there are newly emerging load peaks in the early morning hours and also in the afternoon. We also see that in spring and fall, but not to such a great extent, because of course we have a lower heat demand in spring and fall than in winter. So we don't see that those high load peaks. And we also see that for the low scenario, the shift into the early morning hours is smaller than for the other scenarios. That is because of the relationship between the price time series, or the price difference, and the temperature dependent COP and the temperature dependent supply temperature. So for the heat pump itself, we do achieve a better COP in during daytime because we have higher temperatures, or we usually do have higher temperatures than at nighttime. But at the same time, we have the lowest prices in the early morning hours. But those low prices with the let's say worse COP can only be utilized, or if the price spread is high enough. That's why the peaks are higher in the morning hours with the medium and high scenario. So now let's see what happens when we add a PV system to those households. In general, we can see that the load shifting takes place 2 times with PV generation. We don't see such a huge orientation towards the electricity prices anymore. We only see a low increase in peak loads for the households, so it's not that bad for the grid anymore, presumably. But in winter, we do see a little bit stronger orientation to the electricity prices. So we see the load shift to the early morning hours, which is due to the combination of lower PV generation in winter and higher heat demand. So if we now further add a battery storage system, then we get the following results. For all 3, in general, we do see similar effects for the households with heat pump, PV system, and battery system, as for households with heat pumps and PV systems. But we also see in winter a stronger or even stronger orientation towards the electricity prices, which is the difference is due to the usage of the energy from the PV system for the battery system. So that shifts the whole thing a little bit.
Sorry, Judith, you have 5 minutes left.
Okay, yeah, I can do that. Yeah, that said, we can now come back to the economic effects. Maybe one more point of information. I only showed the time series now. We also see an increase in self-consumption and for households using the dynamic tariff. That's another point of information. I couldn't put it on a slide because then it would be too long. But, yeah, so for the economic effects, we do assume metering point operation costs of €7.50 per month and an invest sum for the home energy management system of about €1,500, and with a considered lifetime of 10 years and an interest rate of 2%, that would make around €167 per year. So this means that the savings on the electricity bill when opting for the dynamic tariff and the energy management system have to be at least €257 for a household in order to get an overall cost reduction. Without those additional costs, when we only look at the electricity bill itself, we do see a cost reduction for almost all households in all scenarios. There are 2 exceptions, but it's really not much. But with the additional costs, we can see the results here on the right side in the figure. Depicted is as before in the beginning of the results, the share of households that see a cost increase here in blue, and the share of households that see a cost reduction in green, when they opt for the dynamic tariff and the energy management system. Yeah, we can see that, as we saw before, that there's no household with a cost reduction in the case of the low scenario with households for with only heat pumps. But if we add a PV system and battery system, then we see some changes. So we can see cost reductions for all 3 scenarios, which is due to the combination of the utilization of the energy management systems for the dynamic tariffs, but also to increase self-consumption. And again, we see that for the higher the price scenario, the more households get a cost reduction. So those were the results. Now we'll give a short summary and go on with the discussion and outlook in 2 minutes. Yeah, so the first research question that I showed was what are the effects of the changes in the spot market for the economic attractiveness of using a home energy management system for household customers. So we see that dynamic tariffs in combination with a home energy management system can lead to cost reduction for household electricity bills. This effect is highest for households with an electric vehicle and a heat pump combined. But we also saw that the cost savings on an electricity bill need to be high enough to compensate for the invest in the energy management system and the metering point operation costs. Also, we saw, especially for heat pumps, that we can increase or establish cost savings for households with heat pumps when we also add a PV system and or a battery storage system. And also we saw that the higher the price scenario and the price spread, the more attractive it is to use dynamic tariffs in combination with the energy management system. What does that mean for flexibility deployment of different technology assets in households? We did focus on heat pumps here. So we saw that we saw an increase in peak load in the early morning hours and in the afternoon, especially in winter. And we saw for households with PV system and or battery storage system, we saw a slight increase in peak load in the morning hours, but not as big as for households without those assets. Okay, that's my last slide. To further investigate the topic of flexibility utilization of heat pumps when using dynamic tariffs, I think it would be interesting not only to have a look at air-water heat pumps, but for the German case, we also have a lot of brine water heat pumps. So it would be interesting to look at those because they don't have a COP that is dependent on the outside temperature. So the flexibility utilization there might cause higher peak loads in the low price times in the morning hours. But of course, that depends on, also on, for example, on the size of the heat storage tank, etc. So it would be interesting to further investigate that. Another interesting point would be to analyze the effect of dynamic tariffs for households with heat pumps and PV systems or battery storage systems further by comparing it to the case that we have households with those technologies with an existing energy management system, but a static tariff to see the real effect of the dynamic tariffs itself. And not only focusing on heat pumps, the next step will be to also analyze the results deeper for electric vehicles and battery storage systems. And I think in future work, I want to combine this analysis with an investigation on the effects of power distribution networks and the grid expansion considerations. And yeah, thank you for your attentions.
Thank you for your presentation, Judith. So now it's time for Xin Ben from the University of Geneva. She will present a paper using the retrospective modeling to inform choices in developing bottom-up electricity system models. Please, Xin.
Thank you. Can you see my screen?
Yes, we can see.
Yeah. Thanks for being here for my presentation today. I'm going to talk about how we can use the retrospective modeling to inform choices in developing a bottom-up electricity system models. So starting from the background of the study, so in our aim is to use the retrospective modeling and the hindcasting and the model evaluation to find some insights on like what can we get from the past. So the retrospective modeling is often used for model evaluation to see what can we learn from the, for example, how accurate the model captures the real world transitions in the past and how we can improve the models based on our findings and observations. For example, in the previous study of Evelina Tuknevich in 2016, this example in UK, they have compared the real-world transition with the cost optimal scenarios within the exogenous demand and investment cost. So we can observe here a cost deviation of 16% less in the cost optimal scenario compared to the real-world transition. So and also we find that there is a different technology mix and capacity mix. And the question is, what if we consider endogenous functions? For example, what if we consider the endogenous demand and endogenous technology learning in the model? What the deviation will look like regarding the cost and the technology deployment. So in the past, most retrospective modeling studies focus on one country or one region, but there are practically no studies for assessing multiple countries in parallel. And also on the other hand, empirical research on integrating endogenous demand and technology learning effect in the energy system models, or the integrated assessment models have focused on the price elasticity of energy demand is dependent on countries, and also some energy shocks, energy crisis, and energy products. And also we found that the optical remains in terms of how to estimate the key parameters of endogenous learning effect under uncertainties. And also there are very limited country-specific evidence on the impact of endogenous functions on overall electricity system performance. So that raises research questions like, for example, how to evaluate the retrospective performance of the different model versions, like if we include endogenous demand or endogenous technology learning, what's the difference between the exogenous assumptions? And the second is for each country, which model version are suitable to represent the real-world dynamics, like which one perform better than others, and how can we choose the model version for different countries. And the third is what should be considered when making decisions which model version to use for projection in a certain country. So if we go to if we begin with the method by looking at the retrospective modeling of national electricity transition. So the first step we do is historical data collection regarding the national electricity system transitions in Europe in the past 30 years for 31 countries. And then the input is set into the D-expense model, which is a dynamic version of exploration of patterns near to optimal energy scenarios. And so we use, this is an electricity sector model. We use 4 cost optimization model versions, which is model basic version without any endogenous functions included. And also we have version with endogenous demand, and version with endogenous technology learning, and version with both endogenous functions. And by doing that, we can obtain a least cost pathway in 4 model versions from 1990 to 2019. And in the meantime, we can get the historical pathways, and we can get the deviations in 31 national models, EU27, UK, Switzerland, Norway, and Iceland. And then the deviations are set as input to the accuracy model, which is we calculate the error, we quantify the error with the preferred accuracy indicators based on the 4 criteria: effectiveness, robustness, compatibility, and diversity of the indicators. And if we look in detail about the how we endogenize the demand and the technology learning effect. So the first thing is endogenous demand, that we consider the supply demand economic equilibrium, and we set the electricity price elasticity based on the literature review for the electricity sector. And on the other hand, we set the endogenous learning effect endogenously with assumption that the investment cost will reduce if we have if we install the capacity of each technology. So we have a learning rate for the gas, the CCGT, nuclear, onshore wind, offshore wind, solar PV, and biomass. So, sorry. Come to the results. First, we want to know that what's the least cost pathways looks like and how it's different from the real world transitions. For example, in Spain, we observed that there are quite different behavior regarding the capacity and annual generation. So this is a real world. We see that there are yeah, so compared with the real world, our cost optimal scenarios, we can observe that there are much less, for example, onshore wind is missed in the cost optimal scenario because it's not cost efficient in the past. And so the model chose not to install any of them. And also we found that compared to the real world, there are much less gas in terms of the capacity and generation. And if we observe the endogenous demand version, we found that electricity demand is overall well captured in the model, except in the long run. But the elasticity was chosen to be close to reality. So it really depends on the assumption of the elasticity factor. And if we observe the version with technology learning, and we found that if we use in endogenous technology learning, and then we can find that the onshore wind capacity and generation accuracy is increased because, like in the model with endogenous technology learning, we will find that the onshore wind cost will reduce with the capacity installation. So the model will have like a relatively lower cost regarding the onshore wind compared to other technologies. So that's why we have a bit increased accuracy regarding the onshore wind. However, we found another issue is that the takeoff year of the onshore wind is not well estimated. So it's we sometimes, because of this inaccuracy in the model, we cannot exactly estimate 100% sure when the technology will begin. And regarding the CO2 emissions, we found that they are underestimated because we always have over-projection of the nuclear or the over-projection of the onshore wind in different model versions. Regarding the model evaluation, we first once we have the deviations of the model, and then we will use 24 different accuracy indicators to quantify the errors. For example, based on our literature review of the accuracy indicators, which is used in the past electricity or energy models, we can have 5 categories of indicators, which is directional indicator, which means that we have we can observe the under projection or over projection of the projection, because we don't calculate the absolute value. It's like a relatively value. And the second category is absolute indicators, which means that we calculate the absolute value of the error. And the third category is median. So in the median indicator, we calculate the median instead of the mean of the error. And the squared means that we want to know that what's the impact of outliers. So it kind of amplifies the outlier effect. So if we have a very high error occurred, then the total mean error will also increase. And also we have unpredictability and gross error calculated to show that the errors within a time series. So the next step we do is that we want to know that in overall 31 countries and for all the quantities that we observe and quantify, what are the most effective small indicator sets that we can use for the model evaluation. So we do correlation-based dissimilarity analysis, and we try to find a small set of indicators that we can use for the future accuracy and model evaluation. Okay. So we found that the most suitable set of indicators is this 5 symmetric mean percentage error, symmetric mean absolute percentage error, symmetric median absolute percentage error, and root mean square logarithmic error, and gross error.
Sorry, Xin, you have 5 minutes left.
Yeah, thank you. I think error is enough, I hope. Yeah, so I think this is the last figure of results. So the key information from this figure is that since we are looking at the difference between the 4 versions that we compare, and we want to know that what information can we get from these 5 indicators. And so we found that for these 3 indicators with the endogenous assumptions, we can improve these 3 indicators. However, there are 4 indicators. However, the gross error is increased, which means that, in other words, is the performance of the gross error has reduced because of the endogenizing the learning effect. So it's really a matter of how we what's the indicator that we focus on. Okay, so I will skip this and do the conclusion. From our study, we found that endogenous demand can overall capture the real world, real demand trend, but it is greatly dependent on the national elasticity factor assumptions. And on the other hand, the endogenous technology learning in our model potentially in other cost optimization model cannot always capture the technology transitions, because we cannot always capture the breakthrough of each technologies at a national level. And also we have observed many cases with under projection of renewables technologies, especially solar PV. And for the countries with more decentralized technologies, for example, Denmark, technology learning is more essential than those countries with centralized generation, like in France. And the implication for the future work is that we are going to refine this work. Like more studies should focus on the elasticity of demand. Is it necessary to evaluate the elasticity in a country or region specific situation to get more accurate projections for some countries? For example, the Baltic countries have similar patterns of drastic decrease in electricity demand in 1990s because of the economic transition in post-Soviet time. And that's one situation that we are going to consider, because if we want to learn from the past, then to what extent we should include the information of the past in the model to project the future is a very essential question to answer. And finally, endogenous technology learning functions need to be refined because if we account for global learning or the real-world deployment constraints, like the slow uptake of wind power due to acceptance, like all the socio-technical factors in the model, it will be a totally different story. And I think thank you for your attention. I think I didn't.
Thank you, Xi. Thank you. So now we have our last presentation from Giovanni Bernardo from the University of Naples on the possible ways out of the power market conundrum after the big peak for gas in Europe. Please, Giovanni.
Yeah. Good afternoon all, and thanks for giving us the possibility to present this paper that basically is still in progress, so feel free to give us comment and feedback. This is co-authored with Francesco Marghella. So this is the overview of my presentation. I will first motivate the paper presenting the research question, then I move on methodology, giving a brief explanation on our net model. Then I'm going to discuss the pricing mechanism that we model on our framework, and then scenario analysis and conclusion. So the increase in energy prices began in late 2021 when demand for natural gas began to exceed supply by the effect of post-COVID growth. Europe, in this case, is facing a major energy crisis driven by a natural gas supply reduction following the Russian invasion of Ukraine and the decision to limit the supply of gas to Europe. As a consequence, energy price shocks has caused the rising inflation and deteriorating monetary condition, slowing the growth expectation of European economies. The surge of inflation, of course, has triggered the cost of living crisis across Europe, and governments are intervening to try to protect families and firms from the instability of price electricity. The current situation has brought the rule of price formation in the wholesale electricity markets back to the center of the debate. So there are several proposals for reforming or completing, if you want, the European electricity markets and mitigate the impact on natural gas on electricity bills. Among them, we can divide the proposal made by policymakers and the one that come from academia. From the policymaker side, basically, we can the main policy actually are the TOBE, that is the a measure employed in Spain and Portugal, with a price cap on gas for electricity generation. And on the other side, there is a new measure that comes from the European Commission for a temporary power price cap at 180 euros per megawatt hours. In any case, both policy basically are the attempt to obtain a net electricity price reduction for consumers by taking away producer rents from renewable generator and nuclear power plant. From the academia side, we can see two very interesting proposals by Fabra and Meos et al. In 2022, where basically the idea is to construct a new spot forward power market balance that integrate the current pricing mechanism with the long-term instruments such as PPAs or contract for difference. So the idea, the aim of our paper is to contribute in this debate by evaluating in a quantitative way the possible income of different pricing policy. In particular, we basically take a comparison between the system marginal pricing, that is the actual system, against pay as bid, and two market options. So that is the idea to decoupling the market for fossil and non-fossil energy. And basically what we try to do is also capturing the uncertainty due to the fossil gas prices. And then basically we focus on three different elements that are efficiency, fairness in terms of price and economic impact, and finally on environmental sustainability, especially in the long term. So in order to do this scenario analysis, we use this net model that is also employed originally by my co-author, so Francesco Marghella. And this is a system dynamics based macro simulation model to the Italian economy, tailored to assess the feasibility of current target with an higher penetration of renewable energy. I cannot explain in detail the entire model because it's very big, but this is a graphical representation of the model. And as you can see, we have on the right hand side the macroeconomic part of the model, where there are households, industry, government, and foreign sector that basically interacting together will determine the yearly GDP and also the demand of energy. Of course, the demand of energy has a direct impact on the electricity model. Then the electricity model is divided in between different technologies. So we have like all the fossil and non-fossil technology plus some storage technology. And also we divide the model in zone, because the electricity market in Italy is splitting in 6 different geographical zones. So the model in this sense works in 2 different levels of time resolution and geographical granularity. In particular, the macroeconomic model is defined at national level with yearly variables. And at the other side, the electricity demand is the electricity module is splitting in zone, season, month, and hours. So basically, we have a definition of supply, demand, and prices for each hours of the years. Okay, and of course, this is based on the industry's value added and population. Then the price costs are based on projection for investment costs. So we account for fixed and variable O&M cost, fuel prices, CO2 emission permission, then durability and load profile of each different type of technology. And then the new capacity, because this is a dynamic model, so the new capacity is projected to fulfill the expected growth in electricity demand in line with current installed capacity, but constrained by the profitability of each type of technology. So our investment function is a function of the expected demand, the European renewable energy target, of course, then also is a function of net present value and ROI. In this sense, we can see that each technology compete with the other one in terms of profitability. Okay. Then we also account from the authorization time that in Italy is quite long, and the project failure due to bureaucracy issue. Then our simulation is from 2022 to 2030, even if basically we start from 2050 to see the like the power of the prediction of our model. And of course, we calibrate it for Italy. So moving to the different pricing, we can see the first one is the business as usual. So the system marginal pricing that is determined by sorting in ascending order the marginal cost of each power generation plant and selecting the highest price unit scheduled to meet the demand. In particular, in our model, we basically the pricing is modeled as follows. In the like generally, the hourly price is determined by the gas-fired CCGT plants, but when renewable energy production is enough to cover early demand, the price will be determined by the maximum marginal cost among this generation technology. The second price is the pay as bid. Pay as bid is a well-known system where a producer receive what has been offered in the day-ahead marketplace. In our model, basically, the idea is that the bidding price of fossil power generation plants will be equal to their respective marginal cost. So plus an exogenous markup, while the renewable energy sources bidding prices will be equal to the COE cost plus an endogenous markup that is that has a direct relation with the gas price and an inverse relation with respect to the share of renewable energy production. In the case in which the renewables are able to cover all the demand, so the determination of the price will be different, because instead of betting the LCOE cost, they will use the marginal cost, because there is a competition between different renewables technology. Finally, we have the two markets solution that basically is based on the idea that to split the electricity market in two different sources of power. So we have the thermoelectric one, so fossil thermoelectric plants that bid in a spot market with system marginal price mechanism, and on the other side, that is basically the like a sort of total PPAs for the renewables system. We have renewables that operate in a forward market with long-term contracts in which the price reflects the LCOE cost. In our model, to simplify the mechanism, basically the existing RES plants, in addition to any other incentives, can count on the price that is equal of the LCOE of 2022 for all the technology. For the new plants, we receive a price that is equal to the LCOE plus a 5% markup. We select like this lower markup for a specific reason. The fact is that with this kind of configuration, like we have a kind of risk neutral investment. Normally in finance, when you have an investment like this, the interest rate is very low because basically there is no risk. So for this reason, we select a very low markup, but of course it's possible to do some sensitivity analysis on the markup. Then these are our preliminary results. So firstly, I'll show you the national single price. So in Italian is PUN, that basically in different scenario of gas prices. This is the high gas price scenario. And as you can see, the policy starts in 2023. And in this case, both two markets and the pay-as-bid has a very good effect in the price because it lowers a lot. But if we move in a scenario with low gas prices after 2022, of course, basically the three national single price are quite the same. Then, of course, this is the result in terms of annual energy supply cost. Our prediction for 2022 is achieving 83 billions of euro in Italy in terms of total energy cost. And as you can see, again, of course, accordingly to the national price, there is a saving cost when two markets and pay-as-bid are involved in the market. However, the problem is in terms of capacity, and especially like the problem is that these two configurations do not allow to having a very high level of investment in renewable energy if we have this projection until 2030. So as you can see, the system marginal price will basically consent to achieve the European Union targets, that is like 62% of renewable energy share production, while the other scenario, like in the other case, the new rest capacity is lower respect to the system marginal price. So now I'm going to conclude this discussion. So basically, as we said, pay-as-bid and to markets option reduce the price of energy in a scenario with high gas prices, but it has a negative effect in terms of new rest capacity. The main weakness that we account for are in the case of the pay-as-bid is a potential cannibalization risk when renewables cover an increasing part of electricity demand. Since basically, as I said before, we set the bidding price as like in line with the marginal cost of each renewable technology. And so at certain point, this potential effect will slow down the investment in renewable energy. On the other side, the two market option, it's may induce investment in expensive technology, because basically we have this 5% markup. So if, for instance, if the LCOE of wind offshore is like more than 100 euro per megawatt hours, respect to a photovoltaic that is like, I don't know, for instance, 50 euros. So with this kind of mechanism, we will have more investment in more expensive technology, and of course this can have a negative effect in terms of renewable energy capacity. Another issue that we are trying to account for is about storage technologies that is not. Sorry,
Giovanni, you have 5 minutes left.
Yes, I'm like just 2 minutes and I conclude. So basically, the preliminary result in terms of storage technology show that both pay-as-bid and to market option do not spur investments in storage technology for a different reason. Probably like the probably in the pay-as-bid configuration is the cannibalization risk. So the total level of RES investment is not high enough to ensure investment in storage technology. On the other side, the two markets. So the problem of the two markets option is that we fix a price over time. So there is no difference between, for instance, night and day. So the storage technology cannot account from the arbitrage that potentially could be in store energy during the day and then sell it in the night. Okay, so this is another possible limitation of the two markets configuration. So for this reason, we basically, from our point of view, there is no evidence to suggest a reform of price market mechanism. But what is for us very important is having some short measure to try to cushion the negative effect of electricity price stability on the economy. This basically is a simulation of the two different short-term measures, so the Iberian tope and also the price cap. In the case of Italy in 2022. As you can see, if this kind of policies has been applied this year, so we will have a saving at least about like 20 billions of euro in terms of energy cost. Of course, for Italy, TOP has lots of limitation, and in fact, we assume that there is no export in this case, and this is a very strong assumption. But the power price cap seems to be very promising in terms of energy cost savings, and the result seems to be in line with the TOP. The problem is that, as usual, unfortunately, the European Union act with some delay in time. It's remember me the same stuff that occurred in the 2011 economic crisis. So we have now, after 1 year of crisis, we have this short-term measure. Anyways, so another important thing, it will be to give consumer access to cheap renewables with private contract on power purchases agreements, so PPAs, and also with some contract for differences. And another point that we would like to underline is that like the necessity to streamlining the bureaucracy and speed up the authorization time for renewable projects. Actually, in Italy, there are like more than 300 gigawatt of project on RES, but just I think 3.5 gigawatt will be realized this year. So it is very important that like we speed up this transition process to our renewable energy scenarios. So thank you very much.
Thank you, Giovanni, and thank you again for all the presentations. I wonder if there are some questions, because we have some time for questions.
Sorry, I have a question.
Yes.
Can I ask you a question to Jieyang, please? So you were mentioning in your study you use time varying elasticity. So this is the price elasticity with like a short-term
Yes,
one
please.
instead of.
Sure.
So I was wondering, what's the impact of the time varying elasticity in model that we use long range projection? So, for example, if we compare, if we want to make assumption for 30 years elasticity, do you think your method will like still have some impact, or still worthy of like making efforts to do like a time varying elasticity?
Well, I think this particular method and the results that come out of it are really more relevant to short term. By short term, I mean maybe just a couple of years. The reason that's a personal opinion. The reason I think so is because we're experiencing a lot of changes in the space of electricity overall. On the demand side, you have all sorts of technology. On the generation side, supply side, there's also advances. So I think that, well, I hope that the patterns that we see now will actually change with time. So I wouldn't then take what we find in the current situation, or in fact it's historical data that we use. I wouldn't take that and project it too far in the future, because I would expect things to actually change by then. So for those situations, I wouldn't use this intraday level elasticity. I'd be looking at annual, at least quarterly elasticity in that case. And then if you want to still look at patterns, maybe you could, but it might not be relevant in those situations, I don't think.
Thank you.
Thanks. Thanks for the question.
Are there some other questions? Okay, well then in this case, I want to thank you again for your interesting presentations. Thank you also the organizers of the session. And I'm gonna call the session. So
Thank you all for
everybody.
participating and for your interesting presentation. Thank you.
Thanks very much. Have a good evening.
Thank
Take
you.
care.
Thank you. Bye.
Thank you.
Bye.
Thank you.